Starting in this video, we will talk about Chapter 2, Periodic Fields. Throughout this chapter, P always denotes a prime number, and we will begin by introducing the definitions. And we'll begin by introducing the definition for the ring of periodic integers. And we'll begin by introducing the definition for the ring of periodic integers. For every positive integer n, let an be the ring P mod Pnz. This is a ring of the classes of integers modulo Pn. Note that the identity map on Z will naturally induce a homomorphism from an to an-1. And we denote this map by phi sub n. This is from an to an-1, where an is Z mod Pnz and an-1 is Z mod Pn-1z. This map sends an equivalence class in here represented by an integer x modulo Pn naturally to the corresponding equivalence class in here represented by x modulo Pn-1. So we think of the first x bar as x mod Pn and the second x bar as x mod Pn-1. And this map is induced by the identity map on Z. The map phi sub n is clearly surjective, but it is not injective. And as a ring homomorphism, one may want to ask, what is the kernel of phi sub n? It's not hard to see that the kernel of phi sub n is P-1 an. Namely, those integers in an that are multiples of p to the power n-1. Any integer that is a multiple of p to the power n-1 will automatically be 0 in here, because this is a mod Pn-1. And on the other hand, if an integer is 0 modulo p to the n-1, then it is divisible by p to the n-1, so it must be a multiple of this. So this is also easy to see. Now we see that the sequence forms a projective system indexed by the positive integers. And the ring Zp of periodic integers will be the projective limit of the system defined above. Projective limit, also known as the inverse limit, has a very general definition in category theory. However, it will be a digression for us if I spend lots of time to talk about the projective limits in the language of category theory and the most abstract definition. So what we are going to do here is that we are just going to follow Sayre's approach to make this projective limit explicit, and that will be good enough for our purpose here. Explicitly, by definition, an element of the projective limit is a sequence we use this notation to denote the projective limit of this system an phi n. And an element of this projective limit is a sequence x with infinite many components, all the way down to x1, where xn is an element in an. And phi sub n maps xn to the next one, xn minus 1, for any n bigger or equal to 2. And this is the most important property in this definition. Furthermore, this Zp, defined as a projective limit, also has a ring structure. The addition and multiplication in Zp are defined coordinate by coordinate. For example, if you have two elements in Zp, then their product has components, the products of the corresponding coordinates, and so is their sum. In other words, you can think of Zp as a subring of the product of rings, ans. The product of rings is always naturally a ring, and Zp is considered as the subring of that product ring. And now we have defined the set theoretical structure and the algebraic structure for Zp. We can also define the topological structure on it. If we give each an, which is a finite set, the discrete topology, and this infinite product, the product topology, then the topology on Zp will be the subspace topology inherited from the product topology. Note that since each an is finite, so under the discrete topology, each an is compact. And now by the Tikhonov theorem, we know that any product of compact spaces is always compact. So this product for ans is always compact. And we let Zp inherits the subspace topology from this infinite product, which is a compact space. And it turns out that Zp is a closed subspace of this compact space, and therefore is also compact. And we are going to read this as a claim. And now let us check this. Indeed, let us take an element that lives in this product space, but is not in Zp. And we will show that element has an open neighborhood that has empty intersection with Zp. By definition, because this y is not in Zp, namely not in this projective limit. By definition, it means that element must violate this condition for some n. So we may assume that phi sub n of yn is not equal to yn minus 1 for some n bigger or equal to 2. And now we're going to construct an open neighborhood of this y that has zero intersection with Zp. We take U to be the infinite product of y case, where each yk is defined as follows. If k is equal to n or n minus 1, we're just going to take this capital Y sub k to be the singleton y sub k. Otherwise, we take y sub k to be the whole finite set A sub k. Now, by the definition of the product topology, we know that y sub k is an open subset of this product space. Now let us check that U, defined from above, has empty intersection with ZP. This is very easy to verify because any element in U must take this form, but the phi sub n of yn is not equal to y sub n minus 1 by our assumption. So this means this element cannot be in ZP. Therefore, U is an open neighborhood of this element y that has empty intersection with ZP. Because y is arbitrary, we must have that ZP is a closed subspace by definition. Because it is closed in a compact space, it must be compact as well.